everyone. It's nice to see a good number of you here. It is an absolute pleasure. Are we recording? Oh, we're recording. It's a very huge pleasure to have Kay join us today. And I'm having computer problems. All right, resolved. You know, it's interesting. This opportunity came up, and it was like, yes, we get Kay to share with us where they are at with their research and scientifically what the discoveries have been. Was reflecting. It was 2012 that Kay walked into my office and showed up firmly eager for research experience. Academically driven, disciplined, focused, really paced. It was not a surprise to find out that Kay was actually a cross-country runner. That was kind of showing itself in how they confront life in front of them. And, you know, graduated 4 years later with 4 majors and minors. And if you are at all involved in advising, you happen to know that we have a rule of 3 in Weinberg. So therefore 4 is a number greater than 3. That caused some administrative hoops that were dutifully jumped through. So strengths in earth science, math, ISP, and also gender studies. And really demonstrating the ability to navigate through, especially with the challenge of developing paleo sea level proxy in the Yucatan, using calcite rafts, which secured the Seymour Schlanger Award for their research in 2015. Fun fact, Kay was recently down in November in Mexico, and your experimental berms with PVC floating in the caves are still there, and they're accumulating calcite at an astonishing rate.
Wow.
Your footprint is still in Rio Secreto. But it became pretty clear as you were advancing that you were definitely looking forward to the next big challenge, and you wanted heavily quantitative, mathematically, computationally advanced research, but at the same time, the same field challenge with extreme involvement in field work. And where you ended up was just such a powerful and great place to be, with a PhD with Lisa Beal at the Rosenstiel School of Marine Sciences in physical oceanography. And in the short few years, watching the photos of you come in, big ships, Southern Ocean, some of the most challenging conditions, launching huge arrays of instruments on the backs of those boats in, frankly, extremely just very, very hazardous conditions, and then carrying through with dealing with the vast and complex sets of data that have come in to realize new insight. And so that brings us to where we are right now, where with the seminar, I am curious, why is the Indian Ocean warming so fast? And what does this mean for our big Earth systems and the future of our planet? So I'm really looking forward to what you have to share with us today. Welcome.
Thanks, Trish. It's great to be here on Zoom with you all. Okay, can you see my slides okay? All right, awesome. So as Trish mentioned, I'm going to talk about why the Indian Ocean is warming so rapidly. And I don't usually do this at seminars, but since I went to Northwestern, I also threw in my own little intro. Trish already covered some of this, but I started in 2011 at Northwestern in ISP. My second year, I took Physics of the Earth with Craig Bino, which I thought was a really cool class. I had never really thought about applying the math and physics I was into to, you know, things I could go out and see in the Earth environment. And so then I contacted Trish and started doing research with her, which I really enjoyed. We did a lot of field work. So this was one of the field trips that we were on. And then this was when we bought too much PVC to fit in the car, which ended up making those berms that she mentioned. And so I really liked that part of the work. And I also really liked trying to tie what I was doing into climate change. I took some classes related to climate change with Yarrow Axford along the way too. But I wanted to have more math and physics involved because that's really what I'm stronger in. Chemistry and biology and geology are not my strengths. So I wanted to get more towards math and physics. And so I decided I wanted to get a PhD, I think around December of my senior year, which it turns out is a little bit late. And I'd already missed the deadlines for some of the programs, but it all worked out in the end because I only applied to 3 programs and got into 1, which is, perfect. There's no choice to make. And then I graduated from Northwestern and started at the Rosenstiel School of Marine and Atmospheric Science. It was great. We have a beachfront bar. So this was, I think, in like February. We're all out in shorts at the bar. I also did some research while I was there and focused on physical oceanography of the Indian Ocean. So that's what I'm going to talk about today, is all work for my PhD. And also show some pictures and videos from the work we did at sea. So in my first year in grad school, I spent 2 weeks at sea on a South African ship where we deployed instruments. 2 years later, we went back and retrieved the instruments to get the data from them. And then in 2019, I just wanted to go to sea again. So I found a way to join a cruise of the Southern Ocean that really had nothing to do with my research. I just really like the kind of fieldwork aspects, and it was a lot of fun. And then in 2020, during COVID times, I defended my PhD, and then I've started a postdoc at NC State since then. And now I'm using climate models where we break some of the components of the climate model. So for instance, we make it so that the ocean doesn't feel the effects of changing winds, and we can use that to look at the role that the ocean circulation is playing in climate variability and change. Okay, so now going back to the seminar. So I'm going to talk about why the Indian Ocean is warming so rapidly. And this is work I did with a number of different co-authors. And it was an international collaborative project. So there were people involved from South Africa who also contributed all of the ship times. This was all done on South African vessels. There were some Dutch scientists involved, and then the US contingency from Rasmus. And on the US side, we did a lot of the analyses, but there was a huge amount of logistical work that went into this. We had bad weather, we had pretty much everything that could go wrong, went wrong at some point. And so this work couldn't have been done without the continued support from many people, especially on the South African side, who dealt with getting ship time and getting instruments loaded onto the ship and all of that kind of thing. Okay, so an outline of what I'm going to talk about today is, first off, I'm going to tell you that the Indian Ocean is warming rapidly, if that hadn't already been clear. I'll talk some about the Indian Ocean circulation, and then go into the method that I developed for estimating ocean heat transport, and then go into results of how much heat the Indian Ocean is transporting. I'll touch a little bit on what's happening with the atmosphere, and then talk about the dynamics that have caused the changes in the Indian Ocean heat transport. And then I'll go into some conclusions and implications. Okay, so I want to start with this figure from the IPCC report, which shows how much energy is going into the Earth climate system from 1970 to a little bit after 2010. And no surprise, there's more energy going into the Earth climate system than leaving it. So we have this excess energy gain. But if you see the really small purple bar, that's the atmosphere. So we know global warming's happening, but actually the vast majority of the energy is not going into the atmosphere, it's going into the ocean. And most of this is going into the upper ocean, although there's also some component going into the deep ocean. But if we look at where the ocean is warming, it isn't warming at the same rate everywhere. So this is an estimate where on the left, they're looking at the global ocean warming rate as a function of depth. So you have the upper ocean on the top and then the deep ocean below, which has a different scale bar. The deep ocean is warming more slowly. And then they've broken it down into each of the different ocean basins. And there's a lot of things you can pull out of this about how much the ocean is warming as a function of depth and where it's warming more. But the part I want to highlight is that if you look at the upper ocean, global ocean warming rate, about half of the warming is coming from the Indian Ocean, which is pretty remarkable because the Indian Ocean is also not very big. So if we're talking about a change in the sea surface temperature, for instance, or the upper ocean temperatures, these are much larger changes in the Indian Ocean than in the Atlantic or the Pacific. And so some previous authors have looked at what this looks like in terms of sea surface temperature to try to get an idea what's happening in the Indian Ocean. So here, the colored lines are different sea surface temperature products showing the mean temperature over the Indian Ocean with time. And going back to 1955, it looks like there's kind of some decadal variability in Indian Ocean temperatures until about the year 2000. And then the Indian Ocean has just warmed really rapidly, and you don't really see this decadal signal anymore. And if you look at what this looks like spatially, basically the entire Indian Ocean has warmed really rapidly. Maybe there's a little bit of cooling in the Southwest Indian Ocean, but besides that, it's pretty much rapid warming everywhere. And then you can average this a little bit and look at the warming rate as a function of latitude and depth. And a couple things that you can notice there is that the Indian Ocean is warming down at least to 600 meters depth, probably would continue below that as well. And the maximum warming is subsurface. And so this suggests that, for example, it might not be just purely the atmosphere that's right over the Indian Ocean that's causing this warming, because there's actually a subsurface maximum here. And we care about the rapid Indian Ocean warming because it has some important implications. So locally, about a third of the global population lives along the Indian Ocean rim, and this warming is going to have a lot of impacts for sea level rise, as well as potentially for storms that form over the Indian Ocean. And the Indian Ocean is also home to 30% of the world's coral reefs and 13% of the wild catch fisheries. So it's a small ocean, relatively speaking, but it has a big human impact. And then there's also a global impact to the Indian Ocean warming. So these are results from a publication where the authors take a climate model and they say that the Indian Ocean has to warm faster than the Atlantic or Pacific. So they basically just prescribe a faster warming rate in the Indian Ocean than the Atlantic or Pacific. And what they're showing in the colors is the sea surface temperature response you get from that. And then the contours is the precipitation response. And so if the Indian Ocean warms more rapidly than the Atlantic or Pacific, you get this whole global response. So we'd like to understand if the rapid Indian Ocean warming is going to continue into the future, or maybe it's just been an anomaly over the past 20 years and we don't expect this to continue. Okay, so I want to start from the framework of what could be causing the Indian Ocean warming. So what we have is this equation here with 6 terms. And the term on the right is the change in ocean heat content with time. So we know this is increasing. This is the Indian Ocean warming. And then we have the 6 terms on the right, and we want to figure out which terms are playing a role. So the first term is insolation or shortwave radiation. Second term is infrared or long wave radiation. Then there's sensible heat flux and latent heat flux. And I'm going to lump all 4 of those together and call it air-sea fluxes. And for the most part, I'm going to not consider any of those terms. I'll come back to why later, but I'm going to ignore those and think about the ocean-based terms for now. So the next term is an advection of heat into the box, where the box we're thinking about here is the Indian Ocean. And then the last term is the advection of heat out of the box. Again, thinking about the Indian Ocean as our box here. So when I talk about this last term, the heat transport out of the box, I'm going to call that heat transport. Sorry, the advection of heat out of the box, I'll call the heat transport or the heat export of the Indian Ocean. And then the sum of these 2 terms is the net effect of ocean currents on the heat of the Indian Ocean. So I'm going to call that the heat convergence. So in other words, if you have more heat coming into the Indian Ocean than you have leaving, you have a convergence of heat, and the Indian Ocean would be warming up. Again, neglecting these air-sea fluxes. Okay, so this is what our box looks like, which is the Indian Ocean. And so the term coming into the Indian Ocean is the Indonesian through flow here. And this is a flow of warm waters from the Pacific into the Indian Ocean. And this is something that previous authors have already looked at. So I'm going to use the previous estimates, but I'm not going to do too much analysis of the Indonesian through flow. And mostly what I'm going to focus on is the heat transport out of the Indian Ocean across this line here that's near 36 degrees south. And so we want to come up with an estimate of how much heat is moved out of the Indian Ocean across that line. So to do that, we need to know something about the Indian Ocean circulation and what currents we have going across this line. So in the west, we have the western boundary current, which is the Agulhas current, and it flows southwestward along the coast of South Africa. And this is a narrow, strong, fast, warm current. And so this is going to become important in our estimate. Then we have northward flows across most of the Indian Ocean, which are much weaker. And so this I'm going to call the interior flow, and it makes up the gyre circulation. So basically we have kind of a circular flow of waters with water going southward out of the Agulhas current and then returning back northward into the Indian Ocean. And then at the eastern boundary, we have the Lewin current, which flows southward. And I'll talk about that a little bit later too. And so we're going to come up with an estimate of heat transport across this line here at 36 degrees south and compare it to previous estimates, which are shown by the symbols. So those previous estimates come from 1987, 2002, and 2009. Okay, so previous authors have already looked a little bit at what's happening at the Indonesian through flow where water is coming into the Indian Ocean. So this is a time series going back to 1970. And there is a trend in the Indonesian through flow volume transport since about 1990, or on the right is zoomed into 2004 to 2014. There's a pretty large increase. So these numbers here are in terms of sphere drips. There's been a trend of something like 4 sphere drips over a 10-year period. And 1 sphere drip is 10 to the 6 meters cubed per second. It's a volume transport, and it's a very large volume transport. So all of Earth's rivers combined are about 1 sphere drip. So when I'm talking about sphere drips here, it's a large amount of water. And so these previous authors have argued that the increase in the heat content of the Indian Ocean is because the Indonesian through flow has increased. So they say, you know, there's more water coming in here. We know it's warm water, and the Indian Ocean has heated up. The problem with that argument is we know the Indian Ocean isn't gaining mass. So if more water is coming into the Indian Ocean, it has to be going out somewhere. And so depending where it's going out, we don't necessarily actually get an increase in heat just because there's more water coming into the Indian Ocean. There might just be more water flushing through the system and no convergence of heat. So that's why we want to look at the heat transport of the southern boundary here, and then we can add the heat coming into the Indian Ocean to the heat leaving the Indian Ocean. Okay, so how do we actually calculate this? Our heat transport out of the Indian Ocean is equal to the product of the density of seawater times the specific heat capacity of seawater. And neither of those are constant, but when you take the product of them, it's actually surprisingly constant. So I'm going to pull that out of the integral and call it a constant. And then we're going to take the integral zonally as well as with full depth. So we're integrating from the coast of South Africa here over to the coast of Australia and with the full depth of the ocean. And we're integrating the product of velocity and potential temperature. And because we have that product in the integral, what it means is if we have a change in this heat transport term, it could be due to a change in either of the velocity or the temperature. So we could think that there's been a change in temperature, which is advected by the mean velocity, or a change in velocity, which advects the mean temperature, or a change in the covariance between them. So practically speaking, this means if we want to calculate this integral, we need high accuracy and high resolution measurements of both velocity and temperature, which turns out it takes quite a bit of work because the ocean is pretty big. So traditionally, these estimates have been made about once a decade, estimates of the heat transport. So this is a figure from Lumpkin and Spear, and what they're showing is the heat transport across different sections of the global ocean. And these are in the unit of petawatts, which is 10 to the 15 watts. It's a ton of power, about 1 million nuclear reactors, or about 2,000 times the average US power usage in 2020. So we're talking about a lot of heat here. And looking at this, you know, it looks like they've done pretty good. They have numbers on everything, but each of these estimates that they're showing is just a single time estimate. So there's no idea about the variability or any change over time. So these estimates come from taking a ship across one of these sections, and every 30 to 50 kilometers or so, an instrument called a CTD is lowered almost to the bottom of the ocean. And that measures conductivity, temperature, and depth. And from that, you can get the density of seawater. And then from that, you can calculate velocity. You already have the temperature. and then you can just integrate your product of velocity and temperature across the whole section. CTD looks something like this with the instrument on the bottom, and then you can also take water samples in these bottles and do some chemical analyses. So this is great, and it gives really high accuracy estimates, but the problem is that it's really expensive. To go across the Indian Ocean, it probably takes somewhere between like 60 and 90 days with a team of 30 scientists. Ship costs are really expensive. And so it only happens about once a decade. And maybe that would be okay if the heat transport doesn't vary on short time scales, but it turns out that it does. So if we look at the one location where there have been sustained measurements of ocean heat transport, which is in the North Atlantic here at about 24 degrees north, this is the time series of the heat transport in petawatts with the total as the black line. And you can see that the single time estimate of 1.24 petawatts looks like it's a pretty good, average here out of the time series. But we can also see that there's a lot of variability happening. So this is a 10-year period. And if you imagine we only took 2 samples over this 10-year period, you could think that there's a positive trend or a negative trend or no trend in this time series, depending on when you happen to sample. And so we want to construct a time series of the Indian Ocean heat transport so that we can actually start talking about a trend with some robust idea rather than just happening to sample at a high point and a low point. Okay, so we're going to take a different method than what previous authors have done. And we're going to divide up the Indian Ocean into these different components based upon the optimal way to measure each of them. So thinking again about the Indian Ocean basically as a box, we have the Indonesian through flow coming in, and we're going to use previous studies to estimate that. And then if this face here is at about 36 degrees south, where we have flow coming out of the Indian Ocean, we're going to break it up into 5 different components. So probably the easiest one to calculate is the very upper layer of the ocean, the Ekman layer, where the flow is directly wind driven. And so there are equations. All you need is wind stress, and you can come up with the Ekman transport. Next, probably the biggest component is the upper 2,000 meter interior component. And for this, to calculate the velocity, you need density data. And what we're going to use for that are Argo profiles. So Argo floats are these autonomous robotic floats that are deployed from a ship. They sink down to about 1,000 meters depth, and they drift for 10 days. And then at the end of 10 days, they sink to 2,000 meters depth. And then they come up to the surface, measuring temperature and salinity along the way. When they get to the surface, they send the data to a satellite, and then they continue on the next cycle. And so because they drift for 10 days at 1,000 meters, they get more or less randomly distributed over the global ocean. So it doesn't really matter where they're deployed in the first place. And there's somewhere between 3,000 and 4,000 of these floats out at any point in time. So this was a figure showing where all of the floats were located earlier this week. And these floats have been in use since about the year 2000. And there's been pretty good coverage of the Indian Ocean since about 2007. So we're going to use all of these randomly distributed profiles of temperature and salinity of the Indian Ocean to map the density and the temperature fields across 36 degrees south and come up with the heat transport from Argo floats. And we also threw in some satellite sea surface height. There's a lot of math involved, which I'm not going to go through, but it is possible to do. Okay, so we have that big chunk coming from Argo, which is great. But the problem is it doesn't cover everything. So in particular, the boundary currents are both too narrow and in some places too shallow to be measured by Argo. Because they're relatively fast, if any of the floats gets into them, basically they just get flushed out really fast and you don't come up with very many profiles within the boundary currents. So for the Lewin current, what we're going to do is just use previous estimates. Unfortunately, there's not a lot of data of the Lewin current, but it's not too strong, so it doesn't create much of an error. For the Agulhas current, it is an extremely fast and highly variable current. So it's really important that we have accurate data there. And so for that, we had a dedicated mooring array called the Agulhas System Climate Array, which measured both velocity and temperature. And so what that looked like is something like this, going from the coast of South Africa to about 300 kilometers offshore. We had moorings at these locations A through G. And the reason they go so far offshore is because the Agulhas Current is typically pretty close to the coast, but once or twice a year it meanders offshore. And we want to have data even when it's meandering, which will become important. It turns out the meandering is a very important part of the heat transport. So we can look at a section with depth and then distance offshore of what these moorings look like. And we had lots of different kinds of instruments. There were about 100 instruments total, and they measured temperature, salinity, and velocity. And these are all moving up and down in time as well. So they're all measuring pressure. So there's, again, quite a bit of processing that goes into using all of this to come up with a gridded field of temperature and velocity, but it can be done. And what this looked like, practically speaking, this is one of the instruments we had measuring velocity. And what you do when you're on the ship is unspool a few thousand meters of wire, adding instruments on fairly regularly, as well as these floats that keep the mooring upright as much as possible. And this could take a couple of hours, potentially, depending how long the mooring is. And you start lining it all up behind the ship. And then at the very end, there's an anchor which gets dropped, and that goes down to the bottom of the ocean. You have your mooring standing upright in the water column. I also wanted to show we deployed some of the Argo floats while we were on the ship. Keep that quiet. Which don't look that interesting because it turns out you actually deploy them in the box. But basically for these, what you do is you put the box over the back of the ship while it's moving, and then gently drop it into the ocean. And then once it's in the seawater, the box will disintegrate pretty quickly. And then you have this Argo float, which is going to continue to measure profiles of temperature and salinity of the ocean and give us more data. Okay, so then we came back 2 years later to retrieve the instruments. Some of them get a little bit biofouled, as you can see here. But what happens is just up from the anchor, there's an acoustic release. And so you can send a ping to that acoustic release. The rest of the mooring comes off from the anchor and floats up to the surface because you have those floats every couple hundred meters. And then the hard part is you now have a whole string of instruments that's worth probably several $100,000 at least that's floating in the ocean, and you have to find it and then grab it. And so that looks something like this. So here you can see kind of the string of instruments, and one of the crew members has a grapple hook and is trying to grab them. You also want to do this without hitting the instruments because that's not good for your data return either. I'm not going to go through the whole video because I think it took them like 15 minutes to get it eventually, but you can do this. You get all your instruments on board, and then you can download the data from the instruments. It's not necessarily easy at sea. This is our bunks, which aren't terrible, but you have to make sure you bring everything with you. Here, somebody forgot the cable that can download data from the instruments, so we had to kind of make one out of what was available on the ship. And you can also have really bad weather. So this was one of the days people are holding onto the walls because otherwise you're going to fall over. We had things falling, ships rocking a lot. And this was one of the days that's considered good enough to work still. There were also days where the weather was so bad that no work was getting done. And we destroyed the ship library quite a bit with all the bad weather, and the gym. I did not set foot in the gym, sadly, even though I would have liked to, because got totally destroyed by the ocean. Okay, so now we have data for all of these components of the Indian Ocean, except for this below 2,000 meter interior component. So the Argo floats only go down to about 2,000 meters. The Indian Ocean on average is about 4,000 meters deep. So we're missing this big chunk. And there's some temperature data of the deep ocean, and we can use that. And we figure probably the temperature of the deep ocean doesn't change very quickly, but we also need some velocities. And what we did for that is we assumed that the volume was conserved in the Indian Ocean. So if we know how much water is coming into the Indian Ocean, and we know how much water is going out in each of these other components, we can just calculate the below 2,000 meter interior component as a residual. So in other words, big V here is volume transport. We have the volume transport of the Indonesian through flow and set it equal to the volume transport of all the other components. And I have to say I was very skeptical about this because basically you just have an algebraic equation where you're solving for one of the components. Of course, there are errors in all of these, which I haven't put on here, but I didn't really think it would work out. But it works out surprisingly well. So what I'm showing here is a timeline of the below 2,000 meter transport from all of the previous estimates from 1987, 2002, and 2009. And then our estimate, which comes out to about 10 sphere drips. And maybe it's lower than the estimates from 1987, but it's like right in the ballpark with the most recent previous estimates. So it turns out it works pretty well and it doesn't give too much of an error. Okay, so now we have all this data and we're gonna do two things with it. So we estimated a 2010 to 2019 mean heat transport. And for that, we used all of the data of the Agulhas current that we have, which is 5 years worth of velocity data and 2 years of temperature data. It's definitely not perfect, assuming that 2 years worth of temperature data is representative of the mean, but it's what we had. And then we use a full 10 years worth of Argo profiles. So we have a ton of data of the interior of the Indian Ocean. And then we also estimated a 2-year monthly time series using that 2 years during which we have temperature data of the Agulhas current. And so we make the Agulhas current, the interior, the Ekman, and the Indonesian through flow components vary monthly. The Lewin current, we don't have enough data to make it vary in time, so we just assumed it was constant. And so mostly we're going to use this 2-year time series to try to assess if there's a seasonal cycle in the heat transport and whether that could be aliasing any of the trends we're seeing. I'm not going to go through this table, but we also did a really robust analysis of the size of the errors, including both error and velocity and temperature of every component. And in the end, the error ends up being about 1/10 of a petawatt for the heat transport and a little bit bigger, about 0.15 petawatts for the heat convergence. And why this matters is if we go back to that equation I showed in the beginning, where we have a change in ocean heat content equals the air-sea fluxes plus the heat convergence from the ocean, so the heat transport into the Indian Ocean and the heat transport out of the Indian Ocean. You can imagine if we had all of these terms except one, you can solve for the other terms. So rather than doing what I did and calculate this last term, the heat transport out of the Indian Ocean, we could have used data of air-sea fluxes and try to infer the last term as a residual. But if you try to do that, it turns out that the air-sea flux products really don't agree with each other. So what I'm showing here is 6 different air-sea flux products over the Indian Ocean. Then to the right of that is the mean of the 6, and to the right of that is the standard deviation. And they have some similarities, but it turns out they're pretty different. So if you integrate over the whole Indian Ocean, the ensemble standard deviation of these is 0.75 petawatts. So this is 5 times larger than the error we get from the ocean-based estimate. So I take this to mean if you want to know what's happening with the air-sea fluxes, it's actually much better to measure the ocean and infer the air-sea fluxes as a residual than to trust any of these air-sea flux products. Okay, so now we can talk about the heat transport of the Indian Ocean. We have a volume transport, that's the integrated velocity of each of these components. And then we have a transport weighted temperature, which is just the average temperature considering that the velocities are higher in some areas than others. We want to make sure that the results we get seem like they're reasonable compared to previous authors. So first we look at the inferred circulation of the Indian Ocean and whether it's what we expect. So what I'm showing on the left here is the transport as a function of depth of the Indian Ocean. The thick lines are decadal mean, and then each of the thin lines is each of our 24 monthly estimates. And so what we see for the Agulhas current is that it flows southward at all depths. Southward is the negative here. For the interior, it flows northward down to about 1,600 meters, and then it's weakly southward below. And when you add the two of those up, you get something that's weakly southward at all depths. And that's something we've basically enforced because we've said that there has to be southward flow matching the Indonesian through flow. We also want to check and make sure that the water masses that we think should move northward are moving northward. So in other words, the density of a parcel of water is going to reflect where it was formed. And you can use that to think about whether the flow should be moving northward or southward. So for instance, the really deep, densest waters are coming from Antarctica. And because we know that, they have to be moving northward into the Indian Ocean because Antarctica is to the south of the Indian Ocean. So to do this, we break up the transports into neutral density, which defines these different water masses. And the black bars I'm showing here are our time mean estimate, with the circles being our 24 monthly estimates. The green bars are estimates from a previous study. And so generally speaking, all the previous estimates fall into the range of our monthly estimates for almost all of these different water masses. So that's a good thing. And then we can also use this to come up with a schematic of the circulation in the Indian Ocean. So I'm only showing down to 2,000 meters because we don't have density data below that, but we know that there are deeper waters coming into the Indian Ocean. So positive northward transports here. Those get lighter as they're in the Indian Ocean. And then we also see that there's a northward transport of this layer that's subantarctic mode water into the Indian Ocean. And those also get lighter while they're in the Indian Ocean and exit as surface waters. So what we have is a deep overturning circulation and a shallow overturning circulation. And then there's a smaller cell where red seawater, which is super salty, interacts with some of the waters. Okay, so basically what we see is that we're getting a circulation of the Indian Ocean that's reasonable and it matches with what previous authors have found, generally speaking. And so we think we can trust our heat transport estimates. And so what I'm showing here now is the heat transport out of the Indian Ocean in terms of petawatts, all negative. So they're all southward heat transports out of the Indian Ocean. And I'm showing all the estimates using the data from 1987, 2002, and 2009. And then the open circle is the median from each data set, because there's some big outliers. What we see, our estimate here is this decadal mean from 2010 to 2020. And then we also have this 2-year time series in gray, and the errors are on either side with the dashed lines. And we trust the absolute value of our decadal mean more than we do the 2-year time series because there's a lot more data involved in the decadal mean. So what we see is a heat transport of about 1.1 petawatt southward, which is definitely within the range of what previous authors have seen. But if you do some averaging, it is less than what previous authors have seen. So we think that we're seeing a reduction in the heat transport of the South Indian Ocean. We do want to see if we think the seasonal cycle is playing a role, because each of these previous estimates was only made at one point in time. So maybe they just happen to be at a peak or a trough of the seasonal cycle. But that's where this time series comes in. So because we actually have 24 monthly estimates, we can try to estimate the seasonal cycle of the heat transport. So these black dots here are the monthly mean for each month for the heat transport. The open circles are each of the realizations of each month. There's only 2, definitely not perfect to try to get a seasonal cycle out of 2 years worth of data, but that's what we have. And so the previous estimates were made in November, December, which really doesn't look like it's, at a high or a low of the seasonal cycle. And then March, April, which similarly isn't at a high or a low of the seasonal cycle. So we don't think that that's what's impacting the change in heat transport that we see. Next, we take that heat transport out of the Indian Ocean and we add on the heat transport into the Indian Ocean through the Indonesian through flow, and we come up with a heat convergence. So now this is the impact overall of ocean currents on the convergence or divergence of heat in the Indian Ocean. Okay, so here's where we start to see a real big change. So you can see all of the previous estimates found a divergence of heat, and some of them found a pretty big divergence, like as large as 1 petawatt. What we see is essentially 0 heat convergence. And we also see, based upon our time series, that in any specific month, there can be either a convergence or a divergence of heat within the Indian Ocean. And so this is a pretty radical change here. So again, we want to make sure that the heat convergence that we come up with, we're not just seeing a change because these previous estimates occurred at a single point in time and maybe they alias the seasonal cycle. So we do the same thing as with heat transport, and we estimate a seasonal cycle. So the black dots again are the monthly mean from each month. And here it looks like the seasonal cycle is pretty semi-annual. Previous estimates were in November, December. That doesn't really seem like it's at a peak or a trough of the seasonal cycle. And then in March, April. And March, April does seem like there is a larger heat divergence or a smaller heat convergence than in other times of the year. But this seasonal cycle amplitude is much lower than the change that we're seeing between the previous estimates and our estimate. So we think it might be playing a small role, but even if it is, there's still a really large change in the heat convergence over time. So what we end up getting is a table now where we're using the previous estimates from 1987 and then the mean of all of the previous estimates from the 2000s and as well as our estimate of the mean over the 2010s. And we're looking at the Indonesian through-flow heat transport from each of these, southern boundary heat transport, and the heat convergence. And so what's important is this last row here, where we're showing the 2010s minus the 2000s. So there's been a heat convergence change of 0.6 petawatts. And of that, 2/3 of it has come from an increase in the Indonesian through-flow. And that's something previous authors have already found. Our numbers agree pretty well with theirs. And then the other 1/3 is coming from a decrease in the heat transport out of the Indian Ocean at the southern boundary. Okay, so now we want to actually see if that change in heat convergence could explain the Indian Ocean warming. So we have this term for the change in ocean heat content over time, and that's 0.06 petawatts. You can get a little bit different results depending on what data product you use, but basically it's pretty robustly around 0.06 petawatts. We've ignored this air-sea flux term, and then the change we're seeing in this QV in plus QV out term is 0.6 petawatts. So clearly these two do not agree, just considering that the air-sea flux term is 0, because we're off by an order of magnitude here. And so what this implies is that there's been an increase in ocean heat convergence from the 2000s to the 2010s, but that there must have been a compensating role for air-sea fluxes. So in other words, that the atmosphere must be putting less heat into the Indian Ocean than it was previously. And we tried to confirm this using the air-sea flux data products, but they really don't agree in whether there has been a change or not over the past 20 years. Okay, and then lastly, we would like to understand what dynamics have caused the change in the ocean heat transport at the southern boundary of the Indian Ocean. And there are basically 3 options here. So there's the deep overturning, which is the cell where there's water coming from Antarctica into the Indian Ocean, and then it lightens and exits at shallower depths. Then there's the shallow overturning, where there's mode waters coming into the Indian Ocean, and then they exit as surface waters. And then there's the gyre circulation, which is this horizontal circulation where you have the Agulhas current flowing southward and then interior flow moving northward. So I'm going to step through each of those options. We don't think that the deep overturning is playing a role because we have a flow below 2,000 meters that agrees with previous studies from the 2000s. So if the volume transport is the same of the deep overturning, it probably isn't related to a change in the heat transport. We also don't think that the shallow overturning is playing a role because a recent paper looked at a trend in the shallow overturning circulation And if anything, they see a slight increase in the shallow overturning, and that would be expected to increase the southward heat transport. So it's the wrong sign to explain what we're seeing. And so we think that the gyre has to be playing a role. And so because a major component of the gyre is the western boundary current or the Agulhas current, we can think about what's happened there. The Agulhas current has not strengthened over time, but it has broadened because there's been increasing wind stress at the latitudes of the Agulhas current, and that's increased the amount of eddy kinetic energy in the current, and it leads to it meandering more. And the interesting thing is when the Agulhas current meanders, it doesn't transport more or less water, but it actually transports the same amount of water at cooler temperatures. So your volume transport doesn't change at all, but the heat transport does change. So and we think this is the essential part that's leading to the decrease in the heat transport of the entire Indian Ocean. And so this is really interesting. It's not something that's been seen anywhere else in the global ocean. And it also highlights that it's really important to measure temperature as well as the velocity of these boundary currents. Okay, so in conclusion, with appropriate boundary current monitoring, which is a really big piece, ocean heat transport can be estimated through a combination with Argo and satellite data. And so this implies that you could make estimates like this in other parts of the global ocean, for example, potentially in the Pacific, where this hasn't been done before. It's definitely important that you have appropriate boundary current monitoring, though, because especially the western boundary current often plays a dominant role in the heat transport. And then into the future, those Argo floats that I talked about are being deployed now with biogeochemical sensors. And so from that into the future, we'll be able potentially to talk about things like how much carbon the ocean is moving northward or southward. And then when you do this, your errors are much lower than the errors in air-sea flux products. So that also implies that you could make several estimates like this and try to use it to constrain which of the air-sea flux data products are in best agreement with the independent ocean data. And what we find for the Indian Ocean is that the heat convergence of the Indian Ocean has increased since the 2000s. And about 2/3 of that is due to an increase in the Indonesian through flow. About 1/3 of it is due to a decrease in the southward heat transport out of the basin. And we think that this is fundamentally related to why the Indian Ocean has warmed so rapidly. And we hypothesize that this 1/3 change in the southern boundary of the Indian Ocean is caused by a decrease in southward heat transport caused by the broadening Agulhas current. And so I put most of this in my recent publication in Journal of Physical Oceanography, but there's a ton of methods that I didn't go into too much detail in that are in these 3 other papers if anybody's interested. And I will also take any questions. Thank you. I can't hear you, Trish. Maybe you're muted.
Who's on deck? I see a whole bunch of hands. Let's go with Hannah first. I didn't